Hello and welcome back to another episode of Math with Stone. Today we are going to be doing another linearization problem, but this one's going to be for kinematics. And let's get into it. So what's happening here is we have a steel plate, actually a steel sphere that is being dropped. And we know the distance that it is dropped from. And we have recorded the time that it took to fall. Okay? And if we look here, as we increase the distance, it takes longer to fall. All right. And then the first question says, on the grid, sketch a smooth curve that best represents the student's data. Well, when you get an easy question, take the easy question, draw the smooth curve that would represent that this should be a quadratic expression because the time is typically squared. Okay. And that is all it is for part A. So we are done with part A. The student can use this data for the distance and time to produce a second graph for which the acceleration gravity can be determined. And we want to find gravity. What you want to find typically is either going to be the slope or it is going to be the y-intercept. All right. If only variables d and t were used, what quantity should the student graph in order to produce a linear relationship between the two quantities? So let's think about our kinematic equations first. We have delta x is equal to vi times t plus 1/2, I'm off the page, I'm sorry, g, or acceleration, t squared, that would be provided to you. And they wouldn't put g there, they would put acceleration. And that might be the winner. Let's see if there's another one. Well, actually, that might just be the equation, right? Because the only other ones we got are v final is equal to v initial plus a times t. And nowhere here do we have the ability to represent velocity. So I want to try and avoid equations that have velocity, which this first one that I wrote down has velocity, but what was the initial velocity? It was dropped, so it's 0. So we got delta x is equal to 1/2 gt squared. And this is going to be the equation we use. We do have to make sure that we use the appropriate variables, and they don't want us to use delta x or delta y, they want us to use distance. So it's going to be distance is equal to 1/2 gt squared, and it wants to know what quantities should be graphed to produce a linear graph. Well, I have d as being the y value, so d against a t squared, because this has got to be the x value, and that would mean that the slope would be 1/2 g. Now, you would 100% be allowed to, instead of putting against t squared, you could have put against 1/2 t squared, or you could have put 2d against t squared. You could have gotten rid of that 1/2 in a different way. I have been putting my slope as being the bigger of the things, okay? On the grid, plot the data points and quantities, sketch the line of best grid, label the axes as appropriate. So we have t squared, which would be seconds squared, and then we have d, which is in meters. Okay, got them both. I'm going to have to go up to the thing. I'm going to rewrite the data real quick, kind of maybe put it right here. So we have distance was originally 0.1, then 0.5, I'm off the page, then 1, 1.7, and 2. I'm rewriting the graph so that I can hold them both on the same piece of the camera. Okay, and then time was equal to originally 0.14, 0.32, 0.46, 0.59, and 0.63, and that was in seconds. Now we wanted to plot distance against time squared, so I need to square these times. So t squared would equal, drum roll please, got a lot of calculations to do, 0.14 squared is 0.0196, 0.0196, 0.32 squared. 0.32 squared is 0.1024. 0.46 squared is 0.2116. 0.59 squared is 0.3481. And 0.63 squared is equal to 0.3969. Okay, so that would be the table that we have, and we need to plot this accordingly. They have given us a very long t squared value, and they have given us a relatively short distance value. So we need to go from a distance of 0 to 2. If we need to go from 0 to 2 and it starts at 0.1, that means that I need to scale this appropriately. I think we can count by 0.5s. 0.5, 1, 1.5, 2. That seems pretty good. I don't think I can get much better, but I learned on the last video that pay attention to the scale ahead of time, otherwise you're going to be upset. Okay, but I think that'd be okay. That looks like it'll cover more than half of the graph, which is the requirement. And we need to go from 0.02, which is almost 0, to 0.4. So essentially, I want to try and finish at 0.4. If I'm trying to finish at 0.4, maybe I count by 0.05s. Let's see, 0.05, 0.1, 0.015, 0.2. That would make 0.2 here. If 0.2 is there, then 0.4 would be here. Can I do better than that? Maybe. Let's see. What is 40 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 40 divided by 14 is 0.28. And if you go 0.4 divided by 14, you get 0.028. So maybe we can do 0.03. That might be a bad choice, but I'm doing it anyways. 0.03, 0.06, 0.09, 0.12, 0.15, 0.18, 0.21, 0.24, 0.27, 0.3, 0.33, 0.36, 0.39, 0.42. Okay, so for those of you wondering how I did that, I realized that I had to go from 0 to 0.4 for the t squared here, and I divided that by how many dashes I had, and then I was like, okay, I got that much, and you can't go under that because then it won't fit. So you can round up, and that's what I did. I rounded up the 0.028 to 0.03. Okay, so let's plot the stuff. We got 0.019, which is roughly here, and then it is a distance of 0.1. So 0.019 is here, and 0.1 would be about there. And then 0.1024, 0.1024 is here, and I got to go up to 0.5. That'd be right there. Then we got 0.2116. 0.2116 is here, and then I got to go up to 1, so that's that point right there. 0.34, 0.33 is here. 0.34 is probably there. Actually, it'd be probably closer here. And then it's up to 1.7. So 1.7 is perfectly a little bit lower than half. Then the last point, 0.396. And that is pretty much right there, 0.39, and go over a smidge to there, and then up to 2. Up to 2 on the dot. Line of best fit, I'm going to draw. Try and make sure your dots are above and below. They should give you a clear ruler. Actually, I don't know if they give you a ruler for AP. Maybe provide your own ruler. Try and make sure the y-intercept is 0 because it should be. Now let's see how I did. My line of best fit is okay. I would argue that it shifted maybe down a little bit too much. Plus, I kind of squiggled right there a little bit wrong. We need to pick 2 points that go through perfectly that cannot be the data points. So let's choose that one. That goes through almost perfectly. And then let's choose 0, 0. There's nothing wrong with choosing 0, 0. I don't recommend it. I don't like it, but that's okay. Which means that we can count. We went up by 1.5 and we went over by 0.3. 1.5 over 3, 0.3. 1.5 divided by 0.3 is a slope of 5. Okay. Slope of 5. Remember that the slope is not gravity. The slope was equal to apparently 1/2 gravity. So 5 is equal to 1/2 g. Multiply by 2, divide by 1/2 or multiply by 2, 10 is equal to g, which is definitely just about perfect. Okay? Part E, we had a little bit of time. State one way in which the student could improve the accuracy of the results if the experiment were to be performed again. Explain why this would improve the accuracy. So, not the main point of this unit, but with linearization, if you're at the later part of the year, let's see, we were dropping it, and what we did? We increased the distance that it was taking to fall. What is one thing we could do? It was a recording plate, so that it seems like the timer automatically begins recording with the time of fall. So that definitely was good. And did they repeat their results? They didn't repeat the results. So that's one thing I would say that they could do, is that they could, increase the amount of times that they dropped it from 0.1 and increase the amount of times they dropped it to 0.5, or do a wider array. We went from 0.1 to 0.5 to 1 to 1.7 to 2. Maybe, add a few more distances in. 1, 2, 3, 4, 5 distances is not enough. Repeat the results to increase reliability. That's probably what I would do. And it's only asking for one. Normally, you're expected to design your experiment. And it didn't ask you to do it in a different way. So I agree. Just take more trials to decrease how much variance we have with reliability. Okay? That's going to do it for this one. Until next time, my friends, I will see y'all later. Bye.